Hello everyone, thanks for being here. After the long week we had last week. I'm going to leave the door open because today is quite warm, but if we see that it's too noisy, we might close it at some point. It's a pleasure to introduce you today our speaker, Nathalie Ouellette from Canada. She's the PhD student of Stéphane Courtauld, who's also visiting us for a few weeks here. He's becoming a regular visitor these days. Nathalie, she did her undergraduate in McGill University, where she did a number of pieces of work with different people on cosmological simulations with Ramses, or if I understand here, stellar masses of high redshift galaxies with Tracy Webb. And then she moved to Queens to do her master's, and she's been working on the Virgo cluster. They've been accumulating an impressive amount of data, photometric and also spectroscopic, to do this, to build the best scaling relations we can get from the Virgo cluster. And this is the topic of the presentation today. So it's all yours.
Thank you. So thank you all for coming out. I know that we all had a really big week last week, and thank you also for everyone that helped organize the conference. It was a really great conference, and it was a lot of work, and it really paid off. So I'm going to try to make this as painless as possible, because I know you're all pretty burnt out. So as Jesus said, I'm going to be talking to you about the scaling relations of the Virgo cluster. It's the subject of my PhD thesis that I'm doing at Queen's University with Professor Stéphane Courtauld, who's right there in the room. And we also have a list of collaborators here, most important of which I would say is John Holtzman, who secured a lot of time at APO, which was crucial for a lot of the data that we are using for this thesis. So the formation and evolution of structure is a really important field in astrophysics, and depending on which scale you're looking at, we are doing a good job or a less good job. So as you go to large scale structure, our simulations tend to recreate what we see in observations fairly well. As we go to smaller scales as galaxy clusters, we still do a fairly good job. It's still mostly dark matter, but we're starting to have a harder time reproducing what we see when we go to galaxy scales. So this is an example of how well we do for large-scale structure. This is the 2DF redshift survey, and you can see that it looks very similar to a lot of the cosmological simulations, such as Millennium, that I showed before, and we simulate basically the same kind of filamentary structure in large scale. But as I mentioned, when we go down to galaxy clusters and galaxies individually themselves, we have a harder time having things match between theory and observation. One of the places where we see this mismatch is when we're looking at the velocity function, which is a proxy for the mass function for galaxies. So here you have a plot by Trujillo Gomez, 2011, and these are simulations. And in the dashed lines, you see a compound of observations that they did doing a literature search. And you have an overabundance of dwarfs when you're looking at the theory compared to the data here. And in the large scale, we also have a discrepancy between theory and data. And this is something that we are looking to correct. So the theorists are doing the best that they can to correct things on their end and make the most accurate theories, but observationalists also need to try and make the largest databases that are more carefully assembled together systematically and take out any systematic biases that might be leading to some of these discrepancies that we see again here. This is now from the Alfalfa survey, and this is only late type galaxies, so it's something that we need to add to it. We need to add early types, but we see the discrepancy here again. So how can we do this? We need to have large surveys that look at the parameters of galaxies, and we have a lot of surveys that do this. One of the benchmarks of this is, of course, SDSS, and we've been looking and using this data as a community for a very long time, but we're now evolving into more pointed surveys with more sophisticated instrumentation. So most of you are, of course, familiar with the Khalifa survey. You have MANGA that uses SDSS as well. You have the SAMI survey at the Australian Observatory, and you have Atlas 3D that's been concentrating on early type galaxies. And you have many more, and these are doing hundreds or even thousands of galaxies looking at spectrophotometric data. So this is very important. This is what we need to do, and we're hoping to add to this landscape of large surveys that can help bridge the gap between theory and observations. So we propose that the Virgo cluster is a great place to do that if we choose one specific environment to do it. The Virgo cluster, we're basing ourselves off of the Virgo cluster catalogue by Bengueli et al. 1985, and there's a little over 2,000 galaxies in that catalogue. Of course, when you look beyond that into NGVS now, they're discovering thousands more galaxies in the smaller mass range, but we're sticking to this for now. And this is complete down to -13, a magnitude in the B band of -13. Virgo is a little bit difficult in terms of figuring out the dynamics inside it because it's a very active cluster and there are multiple substructures inside it. So something that would appear as simple as pinning down the distance to Virgo can be difficult because of all of the dynamics, all the activity that's going on inside. But at the same time, because it's still dynamically active, it gives you a unique point of view and it has a cosmologically representative sample of galaxies inside it, whereas many clusters, other clusters, have many more early type galaxies. It's been the subject of many surveys and we're hoping to, again, add to this landscape using the SHIVir Survey. So this is what we're doing now. It stands for Spectroscopic and H-band Imaging of Virgo. And again, we're basing ourselves off of the VCC catalog. We have a subsample of 750 galaxies that all have SDSS photometry in GRI and Z. We emphasize the I band because this is what we mostly use to try and diminish dust effects in all of our scaling relations. We also have novel photometry in the near infrared and the H band that we collected at CFHT for nearly 300 galaxies. And this was started in 2007 by Mike McDonald, who was a former student of Stefan's. And then we add on spectroscopy. So this is where I come in. And we have long slit spectroscopy for about 200 galaxies. I'll describe some of the telescopes that we've used for this. So if you're interested in looking into the SHIVir Survey more, this is the website right here. So the SHIVir Survey, we can see here what our sample is from the McDonald et al. 2009 paper. And all of the colored points are the ones that were observed in the H-band. So you can see they're dispersed throughout Virgo. And we also show here our proportion that we're observing for each morphology type. And we see that we try to stick to proportions that are similar to that of the larger sample in the 750 catalog and Virgo in total, which means that we are really endeavoring to try and have a cosmologically representative sample in our SHIVir survey. So we've used quite a few telescopes to do this, the most important of which up until now has been Apache Point in Sunspot, New Mexico. This is a 4-meter class telescope using, again, long slit spectroscopy. And it was a medium resolution, so we were able to do really great work down to a certain magnitude, especially for the early type galaxies, because early type galaxies started getting very faint, and so we needed to move on later on to Gemini. So we've collected a little bit of data in a campaign last year, and this year at Gemini South, we've been able to go down to better resolution. So we're looking at the lower mass regime. Pushing even further than that, we're looking also at VLT. We recently had a run in April. We're going to see what we can get out of the data that we obtain in April. And this is high resolution, and we should be able to go down to elliptical, dwarf ellipticals that have velocity dispersions on the order of 20 kilometers per second. So really pushing down to low mass. And this is really where we need to start accumulating data, because this is where the discrepancy between data and theory is the greatest, and this is where we have the least data, just because it's harder to collect. Some of the work I've been doing is extracting dynamical profiles from this data. So for elliptical galaxies, or early type galaxies, I've managed to take out velocity dispersion profiles, and here we have an example of 4 different galaxies for which we have the velocity dispersion profile, and you can see that they all have slightly different shapes. The speed at which the slope goes down changes depending on where you are, or some even have what we call a sigma drop profile. So you have a trough at the center, and Comeron et al. And others since then have correlated the frequency of this type of signature with nuclear disks or rings. So you can have kinematic signatures that show different structures inside of your galaxies. Note again here, though, that we go out to very large radii for elliptical galaxies. Typically, people can't really measure velocity dispersion profiles out further than 1 RE because you're doing it all in absorption lines. And to get enough signal to noise to be able to look out there, you need to integrate for many, many hours. So this is one of the advantages of having long slit versus having IFU data. The field of view on IFU data for Virgo typically doesn't really go much further out than 1 RE. Atlas 3D can't go out further than 1 RE because of their field of view. And this is why the SHIVir survey is going to be very complementary to all of the IFU large surveys. This is a stack of all of the velocity dispersion profiles for our galaxies. We put in red, in particular, the ones that we got at Gemini, and we overlap the ones from Atlas 3D, and you can see that we have a similar radial range and sometimes exceeding their radial range. We also have the slug survey, which uses slitlets out to very large. It's different methods, and they concentrate mostly on the radial range outside of 4 RE. But you see that we can go out to quite far often, and you also see, again, diversity of the profile shapes here. So what we are interested in doing is finding a parameter space where we can correlate these different parameters with these profile shapes. We basically want to know why a galaxy has a downward slope, why a galaxy has an upward slope, why it has a trough at the center, why it peaks at the center. So we need to explore all of parameter space to do this. And this is an example taken for 2 specific galaxies. And we're comparing here our results with Atlas 3D, with ACS VCS when we have the data, and slugs. We can see that our radial range matches that of Atlas 3D in the case of M87. So we're doing a lot of work trying to compare our work with those of other surveys to see if we can find any systematic biases between these different methods as well, because in the end we want to compound all of our work with that of the literature to really have a large catalog. But we need to be careful, because if we don't speak to each other as a community, systematic biases can start creeping in. I do a similar study for now late type galaxies. So this is one of our late type galaxies here, and you have here basically a line width for this galaxy. So this is me adding up flux as I go up in radius. So if you can see closely, this peak is actually made up of a bunch of little lines. Each line is me adding up the flux at each radius. So depending on which galaxy you use, you can actually see a sort of shape inside of the peak that follows that of the rotation curve that's overplotted over here. And the red dashed lines are where we will measure the line width, the W20 line width. So you have 80% of the integrated light is between these 2 peaks here. So this is one of the methods that we use to have a velocity metric for late type galaxies. We can also, of course, do just a rotation curve. Our tracer here is H alpha, which is why we sometimes have gaps. But we can still go out fairly far with H alpha. We model this curve using a certain multi-fit parameter function. And we then use this fit to take precise velocity metrics at different radii to then use that in our scaling relations. Here again, we have 2 velocity rotation curves for 2 of our late type galaxies, and we're comparing our work with that of others. So one is a high inclination example, one is a low inclination example. But the main thing that I want to point out here is that we're comparing our sample to that of the Viva H1 survey. So they're using H1, which is usually much more extended than H alpha as a tracer. So here, as you would expect, the H1 rotation curve goes out a lot further. But in this case here, we actually find that the H1 tracer is very short and pretty much the same length as H alpha. It doesn't go much further out. And that's because we find in the Virgo cluster and cluster environments in general, both H1 and H alpha profiles are heavily truncated because of ram pressure stripping in the cluster environment. However, despite that fact, when you do a Tully-Fisher relation using this data, we don't find a marked difference between our Tully-Fisher relation inside the Virgo cluster, or any other cluster really, and that of field galaxies. So here, in the solid lines, in black you have us using a Vmax value for the rotational velocity, and in the red you have us using W20. In the dashed lines you have Tully-Fisher relations from many other compilations that include both cluster and field galaxies, and they all basically fall in the same area. So we don't find a big difference, or any difference really, between the Tully-Fisher relation in the clusters and the field, and this is something that's been observed for about 20 years now, and we're seeing this again for the Virgo cluster. In a similar way, we can do a scaling relation for early type galaxies. So here you have the fundamental plane, you have effective radius here, and some combination of sigma, velocity dispersion and the surface brightness, and one effective radius. And we find that the fundamental plane follows basically the same relation for both giant ellipticals and dwarf ellipticals. So we don't find a large difference. And when we do a careful analysis for the two groups separately, the slope of the relation is essentially the same with an uncertainty. Statistically, it's the same thing. And we compare our result to that of Atlas 3D. They have about 10 times more galaxies than we do, but it's not all in Virgo, of course. And our parameters for the fundamental plane are about the same as theirs. Something we are interested for in these scaling relations, however, is how to diminish the scatter of these. And one way that we could do that is by looking at a third dimension, such as a stellar population parameter like age or metallicity, and trying to find if looking in that dimension can reduce scatter. Or we can look at different velocity metrics that we use in the Tully-Fisher relation. So here we're looking at the Tully-Fisher relation for late type galaxies using Vmax, which is the last observable point where we have a tracer, V2.2, which is at 2.2 disk scale lengths, and V ISO, which is at the 23.5 mag per arc second squared isophoto radius. And we're also comparing with the W20 here again. So we're looking at how the choice of velocity metric changes the scatter of our relation. And here we find that the smallest scatter is found when we use the furthest out velocity metrics. So V ISO is the one that is measured the farthest out, and the scatter is reduced quite substantially. So you have here a scatter of about 0.6, whereas for W20 you have a scatter of nearly 0.9. So it's a pretty significant difference. We do something similar for fundamental plane as well. This is something that's been observed less just because it's a little bit harder to do, especially because ellipticals, again, are harder to observe because of their absorption lines. And we're looking at the fundamental plane scatter, depending on if we use sigma measured at basically the center, RE over 8, at 1 RE, which is typically where people stop because they don't have enough signal farther out. Recent work by the Atlas 3D team and a paper by Scott et al. 2015 say that this is where they find fundamental plane scatter is reduced the most. But we go one step further out and measure it at 2 RE. This is mashed inside of a radius of 2 RE. And we find that the scatter is reduced even further. So compared to it being measured at the center at sigma naught, it's a factor of nearly 2 that it's reduced. And if we compare it to 1 RE, it's a percentage of reduced by about 70%. So it's pretty substantial how much you can reduce the scatter. So the takeaway here is if you go further out, you're including more information from the galaxy. So when we're only measuring at the center, it's not a representative value for the whole galaxy. If you're comparing it to a global parameter like RE or the surface brightness at RE, sigma naught is not really useful in this case. There we go. So this leads us to think that these scaling relations have a lot of wiggle room in a lot of different directions for us to try and truly understand the evolution of galaxies. So this is a paper by Wu et al. 2008, and 2008 was 7 years ago, so people have been doing this for a little while, but it's time that we really push more in this direction now. So they observed, they did a PCA analysis using metallicity as an additional parameter, looking at the fundamental line for local dwarf galaxies. And looking at this third parameter, they can find the difference in scatter depending on these parameters. So you have the paper from Scott et al. 2015 here that showed that scatter was reduced when sigma was measured at RE, and you also have other parameters you can fold in, like age concentration, Sursic index, and morphology, like Tollerud et al. 2011 did here. And they did interesting sort of 3D imaging to try and look at the different relations when you add in additional parameters. But BCA analysis is great because you can sort of dump everything you have in there to try and really understand what's going on in the galaxy. So why do we want to do this? So I don't really need to convince you guys. We all know galaxies are complicated. It's not the way that we used to think about it, where galaxies fall neatly into different categories. We have, again, the great range of different shapes of velocity dispersion profiles that point out different structures inside. So you have signatures that can show you what's going on inside. You have here, from Schauer et al. 2013, you can have little kinematic signatures like a sigma bump here that was seen in simulations a little further out than 1RE that shows that a recent merger has happened in the galaxy. You have kinematically decoupled cores, which can wreak havoc if you don't know what you're dealing with when you're looking at the velocity profiles. And if you're looking at photometry, when you do unsharp masking, you can start seeing that what we thought were simple dwarf ellipticals actually have disky isophotes, so they can have disks embedded inside. Dwarf ellipticals can be often surprisingly blue. So galaxies are very complicated. So we're trying to sort of put all of this together, and it can be a little bit of a nightmare, but we're doing the best we can, and we're trying to find evolutionary scenarios to describe what path a galaxy takes as it evolves. So Capillari et al. 2013 made this plot here, showing the conclusions that they ended on after their analysis of the Atlas 3D catalog, and they're showing the evolution going along lines of basically R is proportional to M. So you have the lines here, and you can see along these lines you have different morphology types. So you can try to figure out an evolutionary scenario going on there. You have a paper from Norris et al. 2014 who does something similar, at least, except they don't talk about the late spirals here, but they go further down in mass and size. And they have suggested evolutionary tracks going from large ellipticals as they get broken down and processed in the cluster environment also, and turn into ultra-compact dwarfs or other galaxy remnants. So we can do the same thing now with our SHIVir survey using both late type and early type galaxies. So this is our version of that now. And under the points, all the points under the circles here are our data, except the large triangles are ultra compact dwarfs taken from the Gehu et al. 2015 paper. And you can see ultra compact dwarfs, they fall pretty neatly inside the galaxy remnants section here. But we are, as far as we know, the first ones to make such an evolutionary scenario plot and have data that for the spirals inside as well. So we see that, yes, the Capillari et al. Paper predicted that the spirals would fall around here, and this is in fact where we see them fall. So we have a large survey that has all the different morphologies for the cluster, for the Virgo cluster, so it shows where each of these fall. You have the zone of avoidance here. Basically, we don't find any galaxies here. No one finds any galaxies here, and it's the same for us. And it's because you max out at some point on the surface brightness density in your galaxy. This is seen in simulations as well, and we don't think a galaxy can survive here past a certain surface brightness density. You have the very low surface brightness density galaxies here, the Malin galaxies here, and there's every reason to believe that a similar zone of avoidance might exist in this area. We could argue that low surface brightness galaxies are very hard to observe as they get to smaller surface brightness, but at some point, some relation related to the escape velocity of galaxies would probably destroy the galaxies here. So there's probably a zone of avoidance to be discovered there as well. These are stellar masses. Yes, they're stellar masses that were computed using color SED fitting. So now adding on additional parameters, as we spoke about before, this is morphology again, but now we've taken out the clouds to make things a little bit more clear. And here we're adding in instead concentration. So you can see pretty clearly that there's an evolution from red to blue in that direction. And you can imagine again the lines that were drawn by Capillary et al. 2013, lines that go down like that. So these are about the same concentration, and as you go up in that direction, they get bluer and bluer, and so less centrally concentrated. So as we look at other parameters, we can see the different correlations come out. Another scaling relation we looked at was sigma versus stellar mass. And this is, we're looking at this section of the Norris figure here. So they were very interested in intermediate masses in the Ames project right here. We're focusing, in our case, in the larger galaxies, really galaxies, because these are globular clusters mostly in stellar systems. And we find, again here, sort of like in the fundamental plane, that the relation for dwarf galaxies and giant dwarf ellipticals and giant ellipticals is essentially the same. Another interesting scaling relation we can look at is the stellar to halo mass relation. This is taken from the Leo2 paper in 2012, and they are looking at the halo mass to stellar mass of clusters and galaxies, and so they have a very large range in halo mass here. And it's this is a dump of a bunch of different literature sources in there, so it's a pretty comprehensive view of the field in 2012 at the very least. But you see that there's quite a dearth of low mass data. When you go down below 10 to the 10 solar masses and stellar mass, there isn't a lot going on here. And again, it's because it's difficult to get that data. But this is what we're trying to focus on, looking at data coming from Gemini and VLT. You can see the curve here that traces the data, and that's because there is a pivot point at which we find that star formation is the most efficient. In this case, it's at about 10 to the 10.4 right here. So we did not use exactly the same axes, so we just flip the thing around. It's essentially the same thing. This is where we have the most efficient star formation. This is the low mass area where we don't have a lot of data. This is our version of it. So all of the pink points are our own novel data, the SHIVir points, and we added on data from other databases as well. You have in yellow the yellow triangles here, again, the Gehu paper. And you can see that there's a small curvature, or at the very least in the low mass end, the spirals from the alfalfa catalog spread out quite a bit. So we find that our most efficient star formation rate seems to occur at about 10 to the 10.3, so about the same area as Leo2 et al. 2012 found. So this is we see the inflection point pretty much at the same space. Again, adding in additional parameters, we look at the morphology here, and the low mass in the other bin, we have dwarf spheroidals, we have irregulars, we have peculiar galaxies, or things that haven't been easily put in a morphology type. You see that the early type galaxies are quite close to the 1-to-1 line. So keep in mind this is dynamical mass, and we measured it only within 1 RE, so we're still in the baryon-dominated range. We don't expect dark matter to really start heavily dominating within 1 RE, and we're comparing it to stellar mass. This is the one-to-one line. The ellipticals tend to fall quite neatly there. As you go down further in mass, the late-type galaxies start diverging off, and you see the curve that we found in Ouellette, and it seems to be a lot due to the late-type galaxies here. Looking again at concentration, you see the early type galaxies that are closer to the one-to-one line tend to be more centrally concentrated. And as you go down, further down, you see that the spirals and spheroidals that live in that part of the diagram are less centrally concentrated. Now we want to add something that talks about stellar populations, so we can talk about the age and the metallicity of the galaxies inside of our catalog. So this is a figure taken from Giroux et al. 2015, and they do a mass size diagram, so RE over stellar mass. And they also added the dwarfs from Toloba and the mostly giant ellipticals from the Atlas 3D survey here. And they find a pretty good correlation in age. These have been smooth, but the correlation is still pretty clearly there. Going from oldest to youngest here, as you move across these lines, you have a sort of similar correlation that you find between using metallicity again, where you have the most metal rich on this end and metal poor there. Because of their catalog, they have a little gap here, but luckily we added more to our catalog and we fill in that gap right here. And we find essentially the same relation, especially for age. So as we go up in this direction, we get to younger galaxies here, mostly the dwarf spheroidals, spiral galaxies, and here you have mostly the ellipticals. When you go to metallicity, it's a little bit messier, but as you go to the spheroidals here, you can still see a slightly bluer area, so there is still a slight correlation that we find. But as we're adding in these parameters, we can start figuring out more complex evolutionary scenarios. So we really need to add in age and metallicity into our catalog and not only restrict ourselves to kinematics. Another thing that we noticed when we looked at our kinematic data this time is that we find a bimodality in the dynamical mass and the circular velocity from which the dynamical mass is computed. This is something that's been known about for almost 20 years now in surface brightness. So in 1997, Tully and Verheyen found for the Ursa Major cluster that there's a bimodality in surface brightness, and this was reconfirmed in 2009 by McDonald et al. And here you have surface brightness, so you see that there's a bimodality in the distribution of surface brightness. This was confirmed again for a larger sample in the S4G catalog by Sorsay et al. 2013. You see that the peaks, they line up at similar points. However, this is I-band, and this is 3.6, so they're slightly different, but you see the bimodality here. A lot of the work has been focused mostly on the bimodality for late-type galaxies, and we have a theory why that might be. There might be probably two stable modes related to the ratio of dark matter to baryons. So there's an uncomfortable point in the center here where galaxies basically don't like to live. They don't like to be there. It's not a stable mode. So they move to either one or the other of the peaks. But McDonald, 2009, found that there's a similar bimodality in early types as well. And we don't really have a proper theory currently to figure out why the bimodality exists in the early type galaxies as well. So in my work in the I-band and H-band, I did a similar study using dynamical mass. And again, you see very clearly, especially if you go in the H-band, there's a bimodality for the late type galaxies and the early type galaxies there. In a global histogram of the whole SHIVir catalog, we see it again here, especially for the early type galaxies. So this is circular velocity, and so it's a histogram. And we're comparing it to the alfalfa survey. And we see the bimodality again, especially in the early type galaxies. But there might be the bimodality there in the late type galaxies as well. And this velocity histogram leads us to somewhere where we'd like to land at the very end, which is the velocity function of the Virgo cluster, and which is what we want to compare with the theory. So eventually we'll have to do completeness correction, especially in the low mass area, to try and turn this into a true velocity function, so that we can, again, go back to the theory and compare, see if the discrepancies are still there. And hopefully, as we added on all of the data from the SHIVir survey and the literature, making the Virgo cluster velocity function, we can help elucidate what's going on here in these discrepant points. So to quickly summarize, give you a summary of everything that I talked about. I introduced to you the SHIVir catalog. It contains SDSS photometry in the G, R, I, and Z bands, and novel photometry taking the H bands from the CFHT telescope. And we have deep optical long slit spectroscopy that allows us to look at velocity dispersion profiles and rotation curves when the tracer allows us to do so at very large radii. And we're very interested in seeing what these velocity dispersion profiles look like between 1 and 4 RE, because this is the regime where you move from baryon to dark matter dominated. And a study by Arnold et al. From the SLUGS team in 2014 found that the characterizations of elliptical galaxies using Atlas 3D data didn't match what they found when they used their slugs data out to further radii. So what a galaxy is telling you at the very center is not necessarily what it's telling you out at its outskirts. So it's important to have a global picture of everything. We found an existence of a variety of profile shapes with many different kinematic signatures. Again, it's important to go further out to see all of these kinematic signatures, and they may be linked to different structural features. They may hint at different evolutionary scenarios. We're starting to see preliminary trends in our scaling relations and our histograms, like the bimodality that we find. And we're confirming a lot of the trends that we see in the literature as well. And we're comparing what people find for the field and for cluster environments. We're working towards building the most complete velocity function for a cluster to date in order to compare that to lambda CDM models and try to figure out why our models on the galaxy scale still have a hard time reproducing data. And everything all together, sort of like as a message to the community, a true understanding of galaxy evolution requires a multi-parameter analysis of not just photometry, but spectrophotometric data. So we really need to come together and then take all of this data and analyze it to try and have a complete view of galaxy evolution. And hopefully, I can add to this picture using the SHIVir survey. Thank you.
Questions?
Yeah, thanks for the very nice talk in a messy, view that we are all in a mess. Okay, so
Yeah.
This is very interesting work, very exciting indeed. Regarding first a comment. Okay, my comment is that all these scaling relations and all these years studies, and many people working on it. I fully agree with you. I mean, there's a lot of uncertainties that come from the accuracy, or the kind of whether you go the inner parts or the outskirts, or so. I agree completely with this, and this needs a lot of work to get the picture.
And a lot of telescope time.
And a lot of telescope time, of course. Regarding and one example is, for example, what I'm going to ask you is regarding the halo mass versus the stellar mass,
Yeah.
And the mess you get is mostly in the low mass systems or the late type systems. And this is, you have determined it through the color, you got I guess the stellar masses through the M/L that comes from the best color fits and so on. They are probably matching it with the single populations. And this becomes a real issue for the systems that have extended the star formation histories, because this bias toward the lower stellar mass. So this is my just one.
Yeah, no, definitely. There's some amount of work being done comparing photometrically determined versus spectroscopically determined stellar masses. I know a lot of people in Khalifa are trying to do that, and you have biases depending on which method you use, depending on the bands you use, depending on the models you use. Even people who do the same, use the same spectroscopic methodology, depending on the models you use, you can end up having different answers depending on where you're looking. So there are tons of different things that can change not only your stellar mass, but your age and your metallicity as well. So you have to be careful, and I think something that's important and a good takeaway message for that is people have to be very transparent about what they're doing, very communicative between each other to make sure you're actually comparing apples to apples when you're talking about these values.
Yeah, no, I have a comment and then a question. The comment is, I think you found essentially pretty much consistent results in scaling relations when comparing different samples, no? For instance, dwarf ellipticals with other early type galaxies more in general, and also field and cluster. So one thing which is quite tricky to me is that usually, the way you derive the fundamental plane is quite dependent also on the distribution of galaxies in the parameter space. So for instance, we saw that if you don't match the velocity distribution on field and cluster galaxies, you get pretty much similar fundamental plane coefficients, but then if you match them, you get some differences popping up. So it's really tricky, the way this goes. And my question is more specific about the scatter around the fundamental plane. Mm-hmm. Many people have found that, this is correlated to stellar population properties like age. In our case, it was alpha over iron, but let's say stellar population. So how do you reconcile this with the reduced scatter when you move to measuring sigma, in larger apertures? And how it goes with the tilt, with respect to the theorem expectation.
This is something that we're just starting, adding in a stellar population parameter like age and metallicity. We're only starting to explore that space now. Most of my master's work in the beginning of my PhD has been focused on where you're measuring the different velocities. But we're definitely interested in doing something like a PCA using age and metallicity to see if that does affect the scatter in fundamental plane and how it affects the scatter.
Relevant parameter.
Sorry?
You should also consider alpha over iron, in the analysis of the scatter. I think it's a very relevant parameter.
Okay.
I mean, at least that's what we found.
Yeah.
More questions?
Yeah, my question is connected to the Tully-Fisher relation.
Mm-hmm.
And the comparison between the field and in the Virgo cluster. I was wondering whether if you see the same slope and what you see is an offset on the towards getting more redder colors, and if you can from there infer something related to how the environment is affected to the star formation histories of the galaxy. So if you have quantified something of that kind.
Yeah. So like the fundamental plane in terms of folding in at least stellar population parameters for Tully-Fisher. That's something that we'll work on. I've been focusing mostly on I-band, but you do see some slight changes in the slope depending on the photometric band that you're using. It's something that I haven't studied in depth yet. In terms of the slopes between, at least in the I-band, between cluster and field galaxies, there's always a certain amount of variation, but we find that they're all the same within their uncertainties when we're comparing to other catalogs. So it seems like the difference in slopes might be due just maybe even the intrinsic scatter inside the Tully-Fisher relation. So within the uncertainties, we find the same slope.
More questions? Claudio?
Just a curiosity, which kind of models, theoretical model, are you comparing to your circular velocity function?
So the model comparison part is going to come at the end once I've corrected my velocity function. We haven't decided yet what we're going to do here. We have close connections to people that work at New Mexico State University. So people like Anatoly Klippin have been doing a lot of work there, and his students. So there's a very good chance that, as I'm not a theorist by trade, we're going to be using collaborators that are theorists, and we still need to discuss what kind of models we want to use in our comparison. So that's something that is on the close by horizon that we're going to need to figure out.
Martin.
It's not a question actually, but just to add to Claudio's question, that the velocity function is almost self-similar in lambda CDM. So it's actually so what you're doing would actually provide an estimate of the Virgo mass cluster. Which will be cool.
More questions?
Oh, no.
No, it's a comment actually for Francesco, but one reason why we're here is to buy stuff from you guys. And one thing that we really need that does not exist in the literature is alpha Orion for Virgo galaxies. If anyone in this room knows how to get that, without the extensive telescope time, we'll take it. But it's actually surprising that most of the large surveys that Nathalie has mentioned don't cover really Virgo that much in terms of getting these data. So if we want to do the job right, we need to get it ourselves or find some good person that's been hiding these data. I don't think they exist actually.
Very good. Anything else? I'll have one.
Sure.
I was curious about something. One of the slides you were showing the rotation curves of an age-on galaxy and a phase-on galaxy.
Yep.
And I found surprising the level of rotation for the phase-on one. So
I mean, these are all inclination corrected.
Okay.
What I was showing was inclination corrected.
Fine. Okay.
But you can see in both cases we have several other catalogs to compare to. So we match, because it's low inclination, it was a little bit harder to wrestle with. But when we do the inclination correction, we match the same general shape as Chemin, which was H alpha, Rubin, H alpha, Viva, H1 in the inner parts. So once you do the inclination correction, it's a little messy, but you can usually get something that's decent out. But we definitely don't take anything that's lower inclination than like 30 degrees, because we're not suicidal either.
Very good. More questions? No? So let's thank Nathalie again for the nice talk.